and at Tau Institute for Alzheimer's Disease Research. After getting her PhD in molecular genetics from the University of Cambridge in the UK, in the lab of Dr. Sidney Brenner, she did a few years of postdoctoral training with Dr. John Hardy in the Department of Biochemistry and Molecular Genetics at Imperial College in London. And then she moved with the lab to the Department of Psychiatry at the University of South Florida, where she was promoted to the rank of assistant professor in 1993. Then she moved as an associate professor to the Mayo Clinic in Florida in 1996, and then to the University of New York in 1998. In 2006, she progressed to her current position of professor at Tau Institute and professor of pathology and cell biology at Columbia University with a tenured appointment. Dr. Dutt has over 100 publications in prestigious international journals, sits on 3 editorial boards, and has received numerous awards in recognition of her scientific achievements, including the Potemkin Prize from the American Academy of Neurology, which is one of the most prestigious in the field of Alzheimer's research. Her research is mainly focused on Alzheimer's disease and the contribution of tangles to disease, and particularly the role of aberrant phosphorylation of specific proteins such as tau in the progression of the disease. Today, Dr. Dutt will present data supporting the targeting of both amyloid and tau to reverse neurodegeneration and cognitive impairment in Alzheimer's disease, and will discuss several therapeutic modulation of autophagy that aim to reduce pathological forms of proteins in the brain. Finally, we will also present exciting data on a new mouse model created to study the spread of the disease. So without taking any further time, let me welcome Dr. Dutt. Sorry, there will be reflection in the library after the question and answer. I noticed that of the Alzheimer's people, you've had Karen Shawash and Mike Hutton come to talk to you about Alzheimer's, and they represent more of the amyloid pathology with Karen Shaw and the tau pathology with Mike Hutton. So I thought it would be quite good if I sort of introduce you to more of the concepts that where we're at now with the field in terms of how we're reconciling the contributions of amyloid and tau, and perhaps what we need to learn from the clinical trial data, the limited clinical trial data we've got so far, and how we should maybe be thinking more about this disease from now on. So just to orientate you, the pathological features of Alzheimer's disease include 2 major lesions in the brain: the extracellular deposit composed of the A-beta peptide. Am I using it? Oh, okay. Composed of the A-beta peptide, which develops in regions involved in memory and in the cortex of the brain too. Intracellular neurofibrillary tangles shown here, composed of abnormal protein tau, which in Alzheimer's disease takes on a particular conformation, the paired helical filament conformation. There's an inflammatory response that occurs concomitant with these lesions, and that includes activated astrocytes and microglia that tend to surround the plaque lesions, a very close association with the plaque lesions. There's also an immune response in terms of complement pathway activated, and all of these features occur in the context of loss of synapses and the development of abnormal cell processes and degeneration of neurons. And the ultimate sequelae of this is the cognitive impairment that's characteristic of Alzheimer's. So the main idea in Alzheimer's disease was that the amyloid plaques are composed of a peptide called A-beta, and A-beta is produced from a type 1 transmembrane protein called the amyloid precursor protein, or APP for short. And the APP was considered very fundamental in the etiology of Alzheimer's for a number of reasons. Firstly, APP is on chromosome 21, and triplication of chromosome 21 leads to Down syndrome, and Alzheimer's is a fairly invariant feature of Down syndrome. And secondly, the APP precursor protein produces a peptide called A-beta, and A-beta is the core of these amyloid plaques. And the pathway by which it's produced is shown here. This is the APP protein, and through a series of enzymatic cuts, you can produce either the A-beta peptide, which is between 40 and 42 amino acids long, or a shorter peptide if this cleavage occurs before this cleavage. So you can generate this A-beta peptide through a number of cleavage events, and that A-beta monomer can go off and aggregate first into dimers, trimers, and ultimately oligomers, and from there it can form into multimeric structures that form the structure of these senile plaques. So this very much implicated ATP processing in Alzheimer's disease, but what really sealed its fate, and the reason why APP and A-beta production is the major target for drug companies and really has been the driving force behind decades of research, was the identification of mutations that occur in the ATP molecule that are associated with, that actually cause Alzheimer's disease. And those mutations can occur either at the N terminus of the molecule, often affecting the cleavage of the base enzyme, or at the C terminal site, affecting the cleavage of the gamma secretase. A number of other genes other than APP have been implicated in Alzheimer's, and actually this C terminus cluster and its gamma secretase was actually found to be the second genetic cause of Alzheimer's disease in that it was found to be the presenilin protein, which is part of the gamma secretase complex, and these proteins all regulate the production of A-beta, or the length of the A-beta produced. So a number of issues actually suggested that ATP processing was the major target, that should be the major target therapeutic, and this has driven the field for many years. So what happens once A-beta is produced? And you'll see I use the word A-beta and amyloid, I often put them together. And this reflects some of the shifts in the rationalization for how Alzheimer's disease is caused. We used to observe amyloid plaques in the brain and try and correlate downstream effects with amyloid plaque formation. But it's become clear that the A-beta peptide, or some oligomeric form of it, is perhaps more responsible for the downstream neurotoxicity than the actual amyloid plaque. So although the amyloid cascade hypothesis, as it was termed by John Hardy and his colleagues a long time ago, although it still refers to amyloid, the amyloid plaque is probably not the neurotoxic lesion, although it definitely contributes to neurotoxicity. It's probably some intermediate form of ATP, such as an oligomeric or dimeric form of A-beta. So the idea here is that A-beta generation, as mutations are sporadic disease, which is the 95% of cases are sporadic rather than familial, A-beta can produce a number of effects, including oxidative stress, excitotoxicity. It aggregates into the plaque lesions, which have a negative effect on the brain in their own right. It evokes an inflammatory response, and importantly, it leads to some effects on tau, which leads to hyperphosphorylation of tau, which is associated with the formation of these neurofibrillary tangles, secondary lesion of Alzheimer's. And Alzheimer's is pathonomically defined as a disease of plaques and tangles. So you get into a little bit of an issue if you try and say someone has Alzheimer's disease and they don't have these two lesions. However, there is a whole subset of Alzheimer's type dementias that only have either plaques or tangles. So downstream of this is, of course, cognitive and behavioral abnormalities and cell death. And so the whole cascade has been related back to A-beta. But I'll go into a little bit where I think this falls down, this whole cascade hypothesis. So I just wanted to show you quickly, and someone had asked me about this model. This is when you make a transgenic to model this disease, classically what we've done is we've taken mutations in an ATP gene or in a presenilin gene, and we've put them into a mouse, and at high enough levels of expression, you can recreate the pathology of Alzheimer's disease. You'll see the plaque pathology, and using specific antibodies, you can see A beta forms that are represented in the human aging brain. You get degenerative structures, you get silver positive, you get thioflavin S positive plaques. And around these, you'll get your microglial response and your microglial and your astrocytic response. And you also get these little dystrophic neurites. This is tau protein staining on the little dystrophic neurites that pop up around the plaque. So we've been able to model the pathology pretty well in mouse models. They were classically done in mouse models for many years. This was the first of the rat models that was produced to model the disease. And in addition to the pathology, we also get, of course, the classic degenerative phenotype. And here you can see an L2P deficit. This is the transgenic and this is the normal. And you can see a deficit in L2P. And you can see a deficit in performance in the water maze. And this is sort of a classic water maze test for memory and learning. And I won't go through this, I'm sure you're pretty familiar with these type of pictures. The ability of the mouse to learn where a platform is using cues around the room as an aid to memory so that it can remember where the platform is. So you see this is represented in both the mouse models and also in this rat model, suggesting that there is an amyloid or a beta-related deficit in both L2P and in memory as the pathology burden increases and as the animals age. So, moving on a little bit from amyloid, it's been discussed a lot, and I would rather concentrate more on tau because I think this is more where the field is moving to. So, to just give you some background information about